Another important dimension of how to think about model building actually is causality, right? What we're generally doing here is we're building models that relate hidden variables to observables. And generally speaking, the relation between those hidden variables and those observables is that there is some kind of hidden process that emits the observables from the hidden process. The hidden variables are, of course, part of that hidden process. Okay? So, maybe there's some kind of complicated process that regulates the weight of a given species of animal. So, if you weigh an elephant, you get a certain mass in kilograms for that particular elephant. You can weigh lots of elephants and you'll get different masses. But, where are those numbers coming from? Well, there's some kind of hidden process that is resulting in different animals, different elephants having different weights. Perhaps we could parameterize or characterize that hidden process by some hidden variables like a mean, a standard deviation. That's choosing a normal distribution as a hidden model. If we had more information about how elephant physiology actually works and elephant genomics and so on, maybe we would start to introduce more interesting, complicated variables that describe that hidden process in a more exact way. But the point is, when we're talking about building models, we are proposing hidden variables, and we are drawing a model for how they emit our observables. Okay? So one way of saying that is we're basically making a causal model. How do the hidden variables cause us to observe certain values of our observables? Okay? So for example, if we say the hidden variable is the mean of some probability distribution that determines weights of elephants, a bigger mean will make the elephant weights that we get from our scale be bigger, right? So the bottom line is that O is observable. Hence, you can measure this likelihood distribution. You can measure that, right? You can say, well, what if we control for H by basically only measuring animals that are elephants? Well, we're going to get a probability distribution that sampled, but we're going to get, we've got that observable, and we just keep measuring elephant weights, and we're going to get some kind of histogram that is basically, by the law of large numbers, going to converge to the probability distribution P of O given H, right? So the key point is likelihoods, or likelihood models, to use the fully general term, are the form that we encode our causality. We basically are going to be proposing likelihood models for how the hidden variables emit the observables. Then, later on, we're probably going to want to do Bayesian type things, right? We're probably going to be interested in making inferences about hidden models and hidden variables, asking questions like, well, I can come up with two different hidden models of the data. Which one is better? Based upon the actual observations that we've made. Maybe one model fits the observations well and the other one doesn't. You're seeing examples of that in your homework. So once we build one of these models that you could think of as the forward direction of the information graph, it always starts from hidden variables and has edges, directed edges, going from hidden variables to observables. Once we build that model, then we're going to use Bayes' law to compute what you might think of as reverse probabilities. In other words, we're going to calculate posterior probabilities of hidden variables given what we observed. And to do that, we just plug in these likelihood models, right? That's what Bayes' law is all about. So that's